Well, you can see this lecture is about finding arc length, or that is finding the length of a curve. And we're not going to approach the problem as you see written out here. But the idea is, if we had a crooked ruler or a flexible ruler, we could measure that curve from P to Q that we were showing right here. Now, of course, when we talk about arc length, we're really thinking about if we could stretch it out and make it flat and then measure it, then what is the length of that curve, as I've shown here. Now, we're going to approach this kind of like we started with finding the area under a curve. We're going to break our problem down into little pieces. So let me put a drawing up here. Well, as you see here, we have a curve. We'll say we want to measure the length of the curve where we're starting at point P and ending at point Q. And of course, the A and B represent the x values from the beginning of the curve to the end of the curve. Now, the curve is going to normally be given to us in terms of a function. So let's assume that that is the function f from x equal a to x equal b. Now, obviously, this wouldn't be a very good way to approximate the length of that curve, but we could approximate it by saying splitting the interval into pieces, or that is splitting the curve into a couple of pieces. And we might look at this, we make a measurement or make pick a position in the middle of the curve somewhere and draw the line segment from P to that point, and then we could draw the line segment from that point to Q. And we can easily measure the length of a straight line. And so we can measure the length of each of these straight lines, and that would give us at least some approximation for the length of that curve. So let me write it down in this way. We can approximate the length of the curve with line segments. This kind of looks like approximating the area under a curve by drawing a few rectangles and measuring the area of each of the rectangles. So we really want to imagine, well, what would happen if we created more line segments? That is, we break the original curve into more pieces. And let me illustrate that with the next drawing. Okay, I've got the curve again here, and now we're going to break this curve into smaller and smaller pieces, and then we'll imagine the line segment direct connecting these two, and then line segment here, and the line segment here, and the line segment here, and so on. And again, we can measure the length of a straight line. And so if we measured the length of each of these straight lines, how many are there? 1, 2, 3, 4, 5. We would have a pretty reasonable, depends on how accurate we want to be, we would have a pretty reasonable estimation for the length of that curve. Now, I've run across a good illustration, actually computer generated, of this scenario. Remember, we're measuring the length of the curve f from x equal a to x equal b. And so I'm going to pause here and see if I can't get those up to show you separately. And then we'll proceed after that. They're just better graphs. I like them. Well, those were pretty good graphs, weren't they? Let's proceed now. Let's imagine that we've broken this line segment into an infinite number of infinitely small, this curve into an infinite number of infinitely small segments, and so we have infinitely small line segments that we need to calculate the length of. And so what I'm doing here, probably I don't really need to draw this on an XY axis. I'm imagining one infinitely small piece of this, and just imagining what that would look like. Well, I'm going to magnify it a lot so I can imagine what I've got. And let's suppose that line segment is lying in here. So here's the line segment that we're talking about. Of course, the curve, you can see the curve part. There's the curve. Let's call, now because this is an infinitely small length, an infinitely small line segment, I'm going to call it by the name ds. And we've seen the idea of this differential ds or dx or whatever as referencing something that is infinitely small in measurement. So the length of that line segment I'm going to call ds. Now, because that line segment is infinitely, and by the way, from this line segment, I'm going to make that be the hypotenuse of a right triangle. Okay? So now I'm looking at a right triangle with an infinitely small hypotenuse. Now, the measurement here horizontally, that is the leg that is horizontal, is also infinitely small, and that's in the direction of x. That's measured along the x-axis. So I'm going to call that leg dx, which is also infinitely small. Now the leg that is vertical right here is measured as a y value, and that leg is also infinitely small because the hypotenuse is infinitely small. So now I've got this triangle, if you will, right triangle labeled. Now let me make some notes over here. What we're going to do is we're going to call, or that is we're going to assume that the length from A to the length of the curve f of x from A to B, that's the assumption we're going to make here, is called S. So we're actually representing the length of the curve as the letter S. And what we've done to the left is we've considered, or we are considering, we consider a single line segment, a single line segment that is infinitely short. Okay, infinitely short. So that means that we have all of our line segments infinitely short, we have an infinite number of those infinitely short line segments. And we've seen this idea before. So as I was saying, I've written it out here, as we have considered before, integration allows us to make an infinite sum, infinite, allows us to make an infinite sum of items with an infinitely small component. So here's what I mean. We've got this infinite number of these infinitely small line segments. And if we add up the length of all those line segments, then that would be the length of the curve. So let me state it this way, that the length of the curve which we called S, would be equal to the integral from A to B, because that's where the line segments start and end, and each line segment has a measurement that we call ds. So all we need to do is integrate all of those infinitely small line segments. Now the question is, though, what is ds? Can we come up with a way to calculate ds? Well, here's what we'll note with, and then we'll go to the next page and work this out a little bit. We'll note, because of the right triangle we have above, that if we square ds, which is a hypotenuse, then that's equal to the sum of the squares of legs. So that would be dx squared plus dy squared. Now from that information, of course, since ds is a length of a line segment, then we can conclude that ds is a positive value, and it would be the positive square root of dx squared plus dy squared. Now this may not seem to be getting us anywhere, but on the next page, after I pause here, on the next page, we'll see the significance of what this does for us. Okay, we have ds is equal to the square root of dx what I'd like to do is underneath the radical, I'd like to factor out a dx squared. So as I do, see underneath the radical, when I factor a dx squared from the first term, I simply get a 1, don't I? Now if I factor a dx squared from the second term, I'm really going to need a dy squared divided by a dx squared. And I factored out a dx squared. So just think about this backwards for me. If I take this dx squared here and I distribute it, dx squared times 1 is dx squared, and dx squared times this fraction of differentials is in fact just dy squared. So I've written something there in a little different way. Now, what this allows me to do is I can break this radical into the product of two radicals. That is, what I have here now is the square root of 1 plus dy squared over dx squared times the square root of simply dx squared. Well, in this first radical, I could really think of this dy squared over dx squared as dy over dx, the fraction squared. And of course, in this case, the square root of dx squared is simply dx. Now, I can't say the square root of an expression squared is the expression unless I know the expression is positive. And remember, dx stands for a distance. Happens to be a horizontal distance, but it's a distance, infinitely small, but it's positive. So what we've written here makes sense. Now, of course, we see that we're left with this situation that ds could be written as the square root of 1 plus, and dy over dx is nothing more than y prime, or the derivative of y with respect to x. So here we have y, 1 plus y prime, the quantity squared, in our dx. Or, if our function is written as in functional form, then this would be the same thing as, that is, ds would be the square root of 1 plus the derivative of f squared dx. Well, we've done a little bit of magic algebra here, but remember, here's where what we were dealing with. We were looking for the length of the curve f of x from a to b. So now we can conclude. Now we have the length of the curve f of x from the x value of a to the x value of b is given by, I'm going to use s for the length of that curve, capital S. Remember, we originally said it was the integral from a to b of ds, where ds is the length of each infinitely small line segment where we're approximating the curve. But above, we found out what ds is. Remember, ds is this expression right here. So we're taking the integral from a to b of the square root of 1 plus the derivative of f squared. And we're taking that with respect to x. So we just replaced ds there. There's the important formula for us to remember. Now, unlike the formulas that we've looked at previously when we were talking about finding a volume of revolution using the disk method or the washer method or the shell method, where we can derive those formulas, this is one we probably won't want to try to derive. We will simply remember this one. I should say one thing here that's not clear in the work that we've done. and that is that the derivative of the function itself, the function clearly, but the derivative of the function itself must be continuous on the interval from a to b. Now, that's generally not something we're too concerned about, but something that we would be aware of. On the interval from a to b, or the interval a comma b, including a and b. So again, that's not written into this, but that is an assumption that we have to make. Okay, well, let's. I need to note here. Let me write some things down. I'll be right back with you. So a note here, as I've called notes from the classroom, which I'll keep using these. The integral above, that is the formula, if you will, for finding the arc length of a curve, often leads to integrals which require specialized techniques to do the integral. The fact that we have that square root, the result that we get, a square root of some kind of expression, we may not know how to integrate easily. So we have to be very careful. In fact, some things we think that we could easily find the length of the curve, when we use this formula, we have real troubles with the integral. Some things that look difficult end up being easy. As I was saying, sometimes we have a difficult time integrating the indefinite integral that we have above in terms of familiar functions. In fact, we'll learn a lot more techniques in the integration techniques, and many times those special techniques are required for this integral. And surprisingly, like I mentioned earlier, some of the simplest functions, even f of x equal x squared, we would have trouble when we looked at the integral, because what would we do? We take the derivative of f and get 2x, and when we square that, we get 4x squared, and we don't really know how to integrate the square root of 1 plus 4x squared with respect to x. We have no technique. So in this section in our homework, there'll be problems that we can do, but there are problems that we won't have posed to us because we don't yet have the techniques. Well, having said that, let me pause, and we'll start on the next page with our first example. Okay, as you can see, our first problem is to find the length of the curve. That is, the length of the graph y equals 4 times x to the power 3 halves from the origin to the point 1 comma 4. That's not necessary every time when we're doing these types of problems to actually have a sketch or a graph, but in this case I've gone ahead and made one. It looks kind of like a parabola, doesn't it? But it's not really a parabola. It looks similar in shape. And this is really just to visualize what's going on. So, and we'll find out later on that some of the curves are so complicated that coming up with a graph would be as much work as finding the length of the curve. But here we go. Let's remember, and I guess I'm going to call L length. That is, I'm going to earlier I was using S, wasn't I? But I'm going to let L represent the length of the curve. And let's just remember the way this goes. Now, in this case, I don't have my function written in functional notation. So remember how it goes, though. The length of the curve that we're talking about is going to be an integral. And we have to know the starting x value. Well, here we see that the starting x value, well, at the point 0, 0, the x value is in fact 0, isn't it? And the point 1 comma 4, the x value is 1. So we're integrating from 0 to 1. And what is it we integrate? Well, we integrate the square root of 1 plus the derivative squared. Well, the derivative in this case we'll write as derivative of y with respect to x, since we don't have any f sitting around. And of course, this whole derivative, this whole integral is with respect to x. So we've got to find out what dy dx is. Okay, so as we look over here, we know, remember that y is 4 times x to the 3/2 power. So the derivative of y with respect to x, what would we do? We'd say, oh, that's 3/2 times 4 times x to the power 1 less than 3/2. Well, 3/2 minus 1 is 1/2, isn't it? And so you see what we actually get is the derivative of y with respect to x is 6x to the power 1/2. Now, let's use this information. I guess I'm going to jump down here, kind of jam myself up a little bit. So let's do this here. L then is equal to the integral from 0 to 1 of the square root of 1 plus our derivative, which is 6x to the power 1/2, but that derivative is squared, and we're integrating with respect to x. Well, just a little simplification underneath the radical, and you'll see that this ends up being the integral from 0 to 1 of the square root of 1 plus. Now, when we square 36x to the power 1/2, well, that's really 36 times the square root of x, and the square root of, 6, squaring of 6, when we square 6, we get 36. And when we square the x to the 1/2 power, we get x. Remember, our x are positive values from 0 to 1, and so certainly when we square the square root, we just get x. So this is the integral that we're worried about. Well, one way we could deal with this is we'll need to do u substitution. But before we do, I'm going to think of this square root as a power of 1/2. I'm thinking of my integral in this form. And from this form, then, I will let u be what I have the power on, 1 plus 36x. And as we know, then, du would simply be 36 dx. So, as we see, as we work on this, we've got an integral from 0 to 1. Now, remember, these are x values, so let's just make sure of that, x value of 0 to an x value of 1. And the reason I'm making a point of that, got an equal there, is because now we have a u to the 1/2, and we have a dx. Now we need to get a du here, and so we see to have a du, we need 36 dx. So as you recall, the way we can deal with that, remembering that these are x values from 0 to 1, to get a du, I need to have a 36 dx. So if I add this factor of 36, it's a factor, if I add this factor of 36 to the integrand, then I can compensate for that by putting a 1 over 36 out here. So my integral becomes the integral of 1 over 36 times, the integral from x equals 0 to x equals 1 of u to the power 1/2 du. Now, I have an option here. I can integrate. Let's go ahead and do that. 1 over 36, the indefinite integral of u to the 1/2 power is u to the 3/2 power, and I know you can figure that out. It's u to the 3/2 power. Now, we need to evaluate that from x equals 0 to x equals 1. Now, we have two options. We can replace u with our x expression, or we can convert our limits x equals 0 to x equals 1 into u values by using the value here we have for u. But I'm choosing to do it maybe in the more standard way, and that is to actually replace u with its original value, that is, u is really 1 plus 36x, and that's to the power 3/2. And that's what we're evaluating from 0 to 1. And since everything's in terms of x, I'm not trying to point that out any longer. So we would simply replace x with 1 first, okay? And when we replace x with 1, you see we'll have a 1 plus 36x times 1, which would just be a 37, and the power on that is 3/2. And when we replace x with 0, we'll just have 1 plus 36 times 0, which is just 1 plus 0, or just 1. So we'll subtract 1 to the power of 3/2. I blew it way back here, didn't I? I'm sorry. I blew it way back here, getting ahead of myself. When we integrate u to the 1/2 power, we get a u to the 3/2 power, but we have to offset that with a 2/3, the reciprocal of our new exponent. And so what does that change? How does that change what we have here? Well, we would end up, instead of 1 over 36, this would be 1 over 54. My bad, I'm sorry about that. See, 1 over 36 times 2/3. Well, we could write that, of course, as the 2 goes into 36 18 times. So this is the same thing as 1 over 18 times 1 over 3. And that's 1 over 54. So we really have a 1 over 54 in this position. I'm so sorry. And we really have a 1 over 54 in this position. So we end up with 1 over 54 times the expression 37 to the 3/2 minus 1 to the 3/2. Well, of course, 1 to the 3/2 is simply 1, isn't it? So this ends up being 1 over 54 times 37 to the 3/2 power minus 1. And of course, we can leave it as an exact value here, which is certainly valid. Or we could now use our calculator and approximate that, and I've done that. And when I approximate it, I get 4.1493. Now, this is by no stretch making it accurate, and sometimes we can't even do this, but I want to point out to you that this is a feasible answer when we go back up and look at our graph. We look at our graph right up here, and what we see is the length of that curve is a little more than 4 units. And if you look, that it's got to be a little bit more than 4 units, because if we had a vertical line from the origin up to 4, that would be 4 units. This is curving its way up there, but it's really not very much of a curve, although I've exaggerated it. So it's feasible that our answer is a little bit more than 4 units. Okay, before we stop this part of the video, this introduction, we'll look at some more examples. But on the next page, I want to point out to you another form of finding the length of a curve. Let's go to the next page. On occasion, we have a function that is written as x is equal to. In that case, we'd actually say that the function is a function of y. That is, x depends on our value of y. So we would have a g of y instead of an f of x. So we're really worried about changing y values. So I've illustrated the problem over here with a little graph. And we would go through the same process that we went through previously, but the results we would get this time is we would have the roles of x and y reversed. That is, this arc length would still, like I said, we'd go through it a little differently, but it would still be an integral of the infinitely small line segments as we break this curve up. But this time, we're moving from a y value of c to a y value of d. As you can see over here, we're talking about y values, and our function is a function of y. So what would happen here is, as we go through the same process that we saw a while ago, we would do a little bit of different factoring out, but we would have the integral from c to d of a square root of 1 plus, now remember we have a function of y, and its x is equal to, so we would take the derivative of x with respect to y rather than the derivative of y with respect to x, and that's what would be squared. And now, of course, again, we're integrating with respect to y. That's the variable that's changing. Or another way for us to write that is the integral from c to d of the square root of 1 plus, and if it's written in function notation, then it's g prime of y that's squared under here with respect to y. So that's just a reminder that we may sometime be faced with things written as x is equal to rather than y is equal to, and we have to change the form a bit. Okay, I'm going to stop this video as an introduction, and then you can look at some of the later videos that give multiple examples, maybe 2 or 3 examples per video. Good luck on looking at those next ones. Hope that you do. Well, as we look at this second example, look straightforward. Find the length of the curve f of x equal x to the 2/3 power between x equals 0 and x equal 8. And you can see I've sketched a graph of this over on the left. And so what we would know is that one of the important components in finding the arc length is that we need the derivative, because we have a square root that has the derivative in it. So we first investigate the derivative. F prime of x here is equal to, let's see, what would it be? 2/3 times x to the power negative 1/3. And of course that would be equal to 2 over 3 times x, the cube root of x. But this is a problem, isn't it? This is undefined when x is equal to 0. And that is, the derivative is. So, but we're going to have to integrate from 0 to 8. And so we've got a big issue here. Well, there's a little technique or a little trick here, because clearly the function is defined at x equals 0. So what I suggest we do by looking at the top of this page is maybe we can solve this for x. That is, let's rewrite this function so that it's a function of y rather than a function of x. I mean, solving it for x. So let's see what we would do then. We would have y is equal to, let's do this, solve for x, and then we'll use a different technique. So what we have now is y is equal to x to the 2/3 power. Oops, 2/3 power. Well, if we're going to solve for x, we need to raise this to the power, what, 3/2? Or well, I guess what we could say that we're going to do is we're going to cube both sides and then take the square root of both sides. So as we cube both sides, we'll have y cubed is equal to x squared. Okay, and then of course we could manage there and say, oh, well then x is equal to the square root of, that is plus or minus the square root of x cubed, which would be plus or minus the square, excuse me, y cubed, I'm sorry, y cubed, which is plus or minus y to the power 3 halves. Now, of course, in our diagram, we see that when x is equal to 0, y is 0, and when x is equal to 8, y is 4. In other words, the y values we're talking about are the positive y values. And so now we have a function in terms of y. That is, x is equal to, and we could call this the function g of y, is equal to y to the power 3 halves. Now we're going to do this integration then in terms of the formula from above. So here's what we would have. The arc length oops, wrote that as one word, didn't I, is equal to the integral from y equals c to y equal d of the square root of 1 plus, and we could write this as d, the derivative of x with respect to y, or we could write it as g prime of y. It really doesn't matter. G prime of y, the quantity squared, and of course we're integrating with respect to y. Well, our c, see, this is our c value, and this is a y value, and this is our d value up here. That's our d value. So this is an integral from 0 to 4, square root of, okay, well now let's see what we get when we find the derivative of g with respect to y. Well, g prime of y, coming right over here, g prime of y, of course, is equal to 3 halves times y to the power 1 half. And then we're going to square that, okay, so what we end up with is g prime of y squared is equal to, what, 3 halves times y to the 1 half squared, which is what, 9/4 times y? So what we have in here is the square root of g prime squared, which is 9/4 times y. We're taking the derivative of that with respect to y. Well, to complete this, we would use u substitution. What we would end up doing is we would let u be the radicand 1 plus 9/4 y. And so du would end up being just 9/4 dy. And so we need to, of course, accommodate that 9/4 by writing 4/9 on the outside of the integral. Of course, here we have the square root of u in this position now, and now we're able to put a du, which was the 9/4 dy, but we've already accommodated that 9/4 by putting the reciprocal as a factor on the outside. And after we go through the process here, of course, remember that these are y values. But after we go through the process here, which I'm convinced that you can complete, I just wanted to show you this idea. We end up with, well, let's see if we can finish this. We end up with 4/9, and the integral of u to the 1/2 power, that's really what we have there, isn't it? U to the 1/2 power, I'll just write this over here. Integral of u to the 1/2 power with respect to u is going to be 2/3 times u to the 3/2 power. And of course, u is that 1 plus 9/4 y. So we have our 2/3 times the square root, times u, which is 1 plus 9/4 y, and we're evaluating that from 0 to 4. Sorry that got messy in there. We can factor out the 2/3, and of course that gives us 8/27, and so we're evaluating now 1 plus 9/4 y from 0 to 4. Of course, when we evaluate it at 4, we get 1 plus 9/4 times 4, which would be, oops, and I'm sorry about all that. That is all to the power 3 halves, isn't it? So we have in here this to the power 3 halves. I apologize that I really bunged that up. And then, of course, like I said, let's come over here. I'm sorry here. So we have our 8/27. When we evaluate at 4, we end up with 1 plus 9/4 times 4, and that's to the power 3 halves, minus, we evaluate it at 0, we just end up with a 1 plus 9/4 times 0, and that's to the power 3 halves. Well, in this first expression, 4 times 9/4 is 9, so 1 plus 9 is 10, so we have 10 to the power 3 halves. And in the second expression, you'll see that we end up with just 1 to the 3 halves power, which is 1. And then well, as we start this video, we're continuing our study of calculating arc lengths of curves. You can see here the problem is find the length of the graph of f of x equal natural log of secant of x from x equals 0 to x equal pi over 4. And so we know how we're going to set this up. We calculate the arc length with an integral. In this case, we're starting our x values at 0, and we're going to an x value of pi over 4. And it's the integral of the square root of 1 plus the derivative of f squared with respect to x. So having knowing that our derivative, our function, is f of x is equal to the natural log of the secant of x, then we need to calculate the derivative. So the derivative in this case, we're going to have to use the chain rule. And of course, the derivative of a logarithm is 1 over the argument. In this case, that argument is the secant of x times the derivative of the argument itself. And so the derivative of secant of x with respect to x, if you recall, is secant of x times tangent of x. And so you can see this will simplify, the derivative simplifies to simply the tangent of x. So here's where we are then. Our arc length, as we put this information in to our formula, if you will, is the integral from 0 to 4 of the square root of 1 plus the derivative squared. And the derivative in this case, of course, I'll just go ahead and write it in again. The derivative, f prime of x squared, and of course with respect to x. And of course, this case that f prime of x is the tangent of x. Oops, I guess I should have said pi over 4 here, my bad. So we have the integral from 0 to pi over 4 of the square root of 1 plus tangent squared x with respect to x. Now, of course, that looks like something that we don't know how to find the derivative, the integral of yet, but we'll note that 1 plus tangent squared of x is equal to secant squared x. That's one of our Pythagorean identities from trigonometry. So that looks like that might be a little easier to deal with. In fact, we ought to be able to take the square root of secant squared x, shouldn't we? So this is the integral from 0 to pi over 4 which is the square root of course, we're replacing 1 plus tangent squared x with secant squared x. Now, we have to be careful here. you know, we get into a habit in earlier algebra classes, in algebra classes, thinking that the square root of a squared is always just equal to a. But this is true only if a is a positive number. Only if a is greater than or equal to 0, actually. So what we normally have to say is that the square root of a squared is actually the absolute value of a. And this is okay. So we have to look over here and consider what we're taking the square root of. And, you know, I guess theoretically, if you will, or practically, we have to say the square root of secant squared x is actually the absolute value of secant of x. But we happen to know that secant of x is greater than or equal to 0. In fact, it's greater than 0 when x, when or on the interval from 0 to pi over 4. In other words, the cosine is always positive on that interval, so the secant of x is also always positive. And so we're clear to say that the square root of secant squared x is just the secant of x. Now, it just dawned on me, you may be thinking, why is he telling me all of this? Well, remember, look where our limits of integration are. They're from 0 to pi over 4. So those are the only x values that we're concerned about here. So now it does make sense, of course, that we can be assured that secant of x is positive on those in that interval, and so the square root of secant squared x is in fact just secant of x. That is a big deal, and we do have to be concerned about it many times, but here we're safe. Okay, so the integral of secant of x, this is one of the integrals that you need to be familiar with in Calculus 2. The integral of secant of x is natural log of the absolute value of secant of x plus tangent of x. Now, as I said, and of course, that's the indefinite integral, and we're needing to evaluate that from an x equals 0 to an x equal pi over 4. Now, the integral of secant of x with respect to x is one of the many integrals that you are expected to know, and I mentioned that at the beginning of the course. Okay, well then let's do our evaluation. So first we'll replace x with pi over 4. So we have the natural log of, here we happen to have the secant of, excuse me, I'm sorry I put this in this position, of pi over 4 minus the tangent of pi over 4, that's replacing x with pi over 4, then minus the natural log of the secant of 0, plus, and I said minus over here, I'm sorry, plus the tangent of 0. Now you might notice that I've not put in the absolute values, and that's once again because we know that the secant of pi over 4 is a positive number, and the tangent of pi over 4 is a positive number. So since we know that, we don't really need the absolute values in this case. And likewise, when x is 0, the secant of 0, secant being 1 over cosine, that's 1 over the cosine of 0, and cosine of 0 is 1, so that's positive. And tangent of 0, well, that's sine of 0 over cosine of 0, where the sine of 0 is 0. So I say that's not positive, but it's certainly not negative. So our argument there is going to be positive. No need for absolute value at this point. Okay, so in this first natural logarithm, we know that the secant of pi over 4 is the square root of 2, and the tangent of pi over 4 is 1. So we have natural log of square root of 2 plus 1 minus the natural log. In the second argument, we know that the secant of 0 is 1, and we know that the tangent of 0 is 1. And then we can simplify a little bit further, because what we do know additionally is that the natural log of 1, and that's what we have here, isn't it? The natural log of 1 is 0. What exponent do you put on e to get 1? And of course that's 0. So our result here is simply the natural log of the square root of 2 plus 1. And if we were trying to get a better idea of the actual length of that curve, we'd use our calculator and say, this is the exact length, of course, but that's approximately 0.88137 units long. So almost 1 unit long. Whoops, units long. So let's pause and go to the next page for example 4. As you see, our example 4, as we continue arc length discussion, is to find the circumference of a circle of radius r. Now, you know the formula. How do we calculate the circumference of a circle of radius r? Well, remember, circumference is 2 pi times the radius. So we know the answer. But of course, we've always just been told that answer. And in this problem, we're going to prove that, in fact, that is the case by calculating the arc length. But we're not going to calculate the length all the way around the circle. We're just going to calculate the length, and we could say calculate the length of half the circle and then double it. Or we could calculate the length of a quarter of a circle and then quadruple it. Or we could calculate the eighth of the way around a circle and then multiply that by 8. And that's actually the method we're going to use. So let me draw a diagram, and then I'll explain to you why as we get through the problem. Let me draw a diagram of part of a circle. Okay, as you can read, for convenience, I'm centering the circle at the origin. And then the equation of that circle would be x squared plus y squared equal r squared. And we're looking at only the part of the circle that is in the first quadrant. And of course, that part of the circle is 1/4 of the entire circumference. Now, what we're actually going to do is we're going to find the length of this piece, which is 1/8 of the circumference. So that length is 1/8 of the circumference. So we're going to find the length there. And then we're going to multiply that result by 8 to get the circumference of the circle. Now, I'm not ready to explain why we're doing that yet, but notice, of course, what I've done is I've drawn a little triangle in here, and the angle that is in this position is pi over 4, or 45 degrees. So that angle is pi over 4. And so what do we know about these positions? Well, if that angle is pi over 4, then we can determine that this length right here is the radius divided by the square root of 2. Now, why would we know that? Because here's what we know, that here's what we know, that the sine, if we think of this triangle, if we think of this as the angle theta, then we know that the sine of theta is equal to, opposite over hypotenuse. We don't really need to know that, do we? Opposite over hypotenuse. And we know that the cosine of theta is equal to adjacent over hypotenuse. Okay? Well, we do know that the hypotenuse, we do know then this information. We do know that the cosine of theta, because theta is pi over 4, the cosine of theta is actually, and we usually write it as the square root of 2 over 2, but that's actually just 1 over the square root of 2. But we'll go ahead and write that in here. Cosine of theta, in this case pi over 4, is the square root of 2 over 2. And the adjacent side of that triangle is what we're actually looking for, that length. And we know the hypotenuse of that triangle is r. And so what we would end up doing here is that we would multiply both sides by r, and we would get the adjacent side, which is that place, which is this side right here, of course. Okay, we would get it is the square root of 2 times an r, all divided by 2. And when we multiply the numerator by the square root of 2 and the denominator by the square root of 2, we end up with, in the numerator, 2 times r, and the denominator 2 times the square root of 2, which you see is r over the square root of 2. So that was the explanation for how we know what that x value is. Okay. Let's see where we are now. We also need to note, we need the information, we need to make a note here, that y squared is equal to r squared minus x squared. Now we're just using the formula for the circle. But from there, we do know also that y is the square root of r squared minus x squared. Now, I didn't say plus or minus because we're dealing in the first quadrant here, and the y's that we're talking about in our diagram for the arc length that we're talking about are all positive y's. And of course, so I said this rather than plus or minus. We don't need plus or minus since it's clear here that y is greater than 0. Okay? That's the reason we don't need that. And of course, we could write this in a fashion that might be convenient, might not be, but when we're finding derivatives, it will be convenient. We're going to write this as r squared minus x squared to the power 1/2. Okay, now we're going to use arc length again, the arc length formula, and so to do that, we'll need to know what y prime is. So we'll calculate y prime, and of course that's the derivative with respect to x. Y prime, looking at our y right here, is going to be 1/2 times r squared minus x squared to the power negative 1/2, then times the derivative of the insides of the parentheses. We're going to get a derivative of r squared minus x squared, which is going to be negative 2x. Now, if we simplify that a little bit, notice that our 2's are going to cancel. We'll have a negative x in the numerator, and that negative 1/2 exponent we'll write as in the denominator as the square root of r squared minus x squared. So that's our derivative. Now, here's exactly the reason that we're using 1/8. We're going to integrate here from an x value of 0, from this x value, okay, to this x value. Stop and think that if we would have integrated from 0 to r, see, if we would have integrated out here to get that whole quarter of a circle, then if you look at our derivative, if we let x be r, we would have the square root of r squared minus r squared, if x is r, and that would be a denominator of 0, and that would be undefined. And so we couldn't, it's not possible, it's not possible to integrate with this expression. It's not possible to integrate this when we're dealing with an x that has a value of r. So that's the reason we're going back to just using this quarter of a circle. We're safe there. Okay, let's set up the arc length formula then. The arc length is an integral, and it's going to be from 0. Now, our x value that we're stopping at is r over the square root of 2. And what are we integrating? The square root of 1 plus y prime squared with respect to x. And we see, of course, over here, well, let's write this in then. Then that's equal to the integral from 0 to r over the square root of 2 of the square root of 1 plus this derivative, which is negative x over the square root of r squared minus x squared, and of course that's squared. Now a little simplification here, and that is we'll actually do the squaring that's under the radical. So we have a square root of 1 plus, and we square this opposite of x, and of course we just get x squared. And then we square that denominator, and we simply get r squared minus x squared. Of course, we're integrating with respect to x. Well, this is going to be messy, but what I suggest is that we change our radicand. Rather than having just a sum, it might be easier if we had a fraction, because we can deal with taking the square root of fractions, because we can take the square root of the numerator and the square root of the denominator. But we can't take the square root of 1 and the square root of that fraction. So we'll create one fraction by adding the 1 with the fraction. So the integral from 0 to the r over the square root of 2, and 1, we need a common denominator, so we're going to write 1 as r squared minus x squared divided by r squared minus x squared. And of course, plus the fraction we already have, x squared over r squared minus x squared. But you notice under the radical, those two fractions, when we add them together, we're going to get a numerator of just r squared. So as I change pages, let me pause here and we'll start up on the next page. Okay, here on this next page, we have the integral from 0 to r over the square root of 2, that's a square root there, of a square root whose numerator now is just r squared, and whose denominator is r squared minus x squared. Now r is a radius, and so it's easy for us to take the square root of r squared since it's positive. So as we continue to simplify here, the square root of r squared, that is the numerator, is just r. The square root of the denominator, well, we can't really perform that square root, so we'll just leave it as square root of r squared minus x squared. Now, of course, x is the variable. And so what we're going to do is we're going to factor out the r from this fraction, thinking of it as r times 1 over the square root. And we're going to factor that constant r. Remember, that's just the radius of the circle. So we're going to factor that r clear to the outside of the radical. The integral, my bad. So we have now just the integral of 1 over the square root of r squared minus x squared. Now, we should recognize this again as one of our special forms. That is, we see it in this form, generally. The integral of 1 over the square root of a squared minus u squared with respect to u. That's the form we normally see, and that's one of the inverse trig forms. Sometimes it's written as arc sine, sometimes it's written as inverse sine, but nevertheless, this is the inverse sine of u divided by a. Now, or, depending on the book that you're using, you might see arc sine. Those mean the same thing. So you remember that. Remembering that then allows us to complete this integral. We have our factor of r on the outside. The integral of 1 over the square root of r squared minus x squared happens to be the inverse sine of x over r. And of course, we're evaluating from 0 to r over the square root of 2. So now we're ready to do our evaluation. Let's see where that puts us. R is on the outside, and we first evaluate at sine over the square root of 2. And in fact, you know, it might have been more useful if I would have left this in the very beginning. You know, on the previous page, we had the square root of 2r divided by 2, and then we rationalized to get this. So this is actually the same thing as the square root of 2 times r over 2. And we might recognize that a little more quickly here in a moment. So we're going to first evaluate it at that x value. And so we have a fraction here that has r as the denominator, and the numerator is the square root of 2 times r divided by 2. Minus, and then we're going to evaluate at 0. So we have the inverse sine of 0. Remember, that's our x value, divided by our constant r. Well, in this first inverse sine, you'll notice that we'll have this will simplify, that is basically will multiply by the reciprocal of r, and I'll let you work out those details, but we'll end up simply getting the square root of 2 over 2. So let me rewrite it here. So that fraction is going to simplify to nothing more than the square root of 2 over 2. And of course here, the fraction simplifies to just 0. Okay, so now what does inverse sine mean? Well, we're looking for the angle that is between negative pi over 2 and positive pi over 2, whose sine is the square root of 2 over 2. And that angle happens to be pi over 4. So the result we get right here is pi over 4. Now, the inverse sine of 0 is the angle that we can take to get to take the sine of and get a result of 0, and that angle is in fact 0 itself. So what we have here, when it's all said and done, is this is pi over 4 times r. Now remember though, this is the length of 1/8 around the circle, or 1/8 of the circumference. Messing that up, aren't I? So the circumference of this circle is going to be 8 times that amount. 8 times pi over 4 times r. And of course, 8 times pi over 4 ends up being 2 pi. So this is 2 pi r, and that's a big, how do you like that? We've proven then that the circumference of a circle using calculus, is 2 pi r, 2 pi times the radius of the circle. Okay, we're going to stop this video, and I'll have an additional video that has additional examples in it about the arc length. Okay, example 5 of calculating arc length, you can read. I'm not sure how clear that is. Find the length of the curve, f of x equal e to the 4x power minus e to the negative 4x power, all divided by 8, on the interval from 0 to 1. And I'm not so interested in the diagram this time. Certainly we could graph that. We could even use our graphing calculator to graph it. But I want to jump right into calculating this arc length. And just for a matter of saving space, rather than writing out arc length, I'm just going to use L for the value of the arc length. So we know here that we're going to calculate an integral from 0 to 1 Those are our x values of the square root of 1 plus the derivative of f squared with respect to x. Now, there's going to be there's a couple of techniques in this. The reason I'm doing this problem, in fact, a technique that you may need to use in your homework, but there's a couple of techniques in here that I want to point out, and so I'm interested in a lot of algebra that's going to go on. Now, obviously, we need to find the f prime of x. And I tell you what I'm going to do first, and this is not so unusual. I'm going to rewrite f of x, and you've seen this idea in Calculus 1. Sometimes we need to rewrite the form of the function so it's more easy to find the derivative. So I'm actually dividing each of those components, each of those terms in the numerator by 8. I'm going to write it as 1/8 times e to the power 4x minus 1/8 times e to the power negative 4x. Now that'll make it a little easier for me to calculate the derivative. So when I do calculate the derivative here, f prime of x, you can see, will be 1/8 times e to the 4x. It'll be 1/8 times the derivative of e to the 4x, which is e to the 4x times 4. So we'll end up with 4/8, or 1/2 times e to the 4x. Now let me remind you again how that happened. The derivative of e to the 4x is e to the 4x times the derivative of the exponent, and the derivative of 4x itself, the exponent, is just 4. So we have e to the 4x times 4, and 1/8 times the 4 is the 1/2. And in a similar fashion, and I'm sorry, I've written down the problem incorrectly. My apologies. We're looking for the length of the curve. Back to the definition of the problem. We're looking for the length of the curve of f of x is equal to e to the 4x plus e to the negative 4x over 8. So that should have been a plus, which means right here we should have had a plus as well. My mistake. Now, when we take the derivative of 1/8 times e to the negative 4x, we're going to get 1/8 times e to the negative 4x, and then the derivative of the negative 4x is negative 4. So we do actually get a minus at this position, and of course we'll have our 1/2 again, and e to the negative 4x power. Now, I have left out some of the details there, but I know that you're a competent calculus student, and so I think you can fill in those details. And one other thing I'm going to do here, though, before I move on, I think this will be convenient later, is I'm going to factor out the 1/2 and say that this is 1/2 times e to the 4x minus e to the negative 4x. I don't make a habit, as you know, of factoring just for the sake of factoring, but you're going to see in a moment when we put this back in for calculating the integral. So here we have now the integral from 0 to 1 of the square root of 1 plus this derivative squared. Now, the derivative is 1/2 times e to the 4x minus e to the negative 4x. Whoops. And again, I've tried to write that ahead of time, and I really made it look ugly. Well, let me rewrite that. That bothers me. I'm sorry. Integral from 0 to 1 of a square root 1 plus, okay, the derivative f prime squared. Well, f prime is 1/2 times e to the 4x power minus e to the negative 4x power. And that all encompasses the derivative, and that's what's being squared. Okay, now I can read it, and I feel better. Now notice that we're squaring a product. So when we square a product, we square each of the factors. And so this ends up being the integral from 0 to 1 of the square root of 1 plus. When we square 1/2, we get 1/4, and then we have e to the 4x minus e to the negative 4x, which is being squared. Okay, well, let's come over here to the side. Let's come right over here and square that e to the 4x. So let's, that e to the 4x minus e to the negative 4x. Let's do that squaring. Of course, that means we're going to have e to the 4x minus e to the negative 4x as a factor twice, times e to the 4x minus e to the negative 4x. Okay, so as we FOIL that, notice that we end up with e to the 4x times e to the 4x. Okay, I'm going to write that down. We're going to come back and talk about that just in a second. And then we'll have e to the 4x times a negative e to the negative 4x. So that'll be a minus e to the 4x times e to the negative 4x. And then we'll have a negative e to the negative 4x times an e to the 4x. Well, so that'll be minus e to the negative 4x times e to the 4x. And then we'll have a minus e to the negative 4x times a minus e to the negative 4x. So that will be a plus e to the negative 4x times another e to the negative 4x. Now, I've crammed that in again, and I apologize. This notebook just doesn't give me the space. Now let's look at this very first term right here. E to the 4x times e to the 4x, what do? We add the exponents when our bases are the same. So this ends up being e to the power 8x. And then in our next expression, e to the 4x times e to the negative 4x, when we add those exponents, 4x plus negative 4x is 0. So this is negative e to the 0. And in the next one, when we add negative 4x and 4x as an exponent, we get 0, so we have minus e to the 0 again. And then in our last term, we have plus e to the negative 8x, my bad, when we add those together. But remember, e to the 0 is 1. So we actually have here e to the 8x minus 1, so I'm going to say minus 2, plus e to the negative 8x. Ooh, okay. So that's the value of this business right here, isn't it? So let's put this into the integral. We have the integral from 0 to 1 of the square root of okay, 1 plus 1/4, and that binomial squared ended up being e to the 8x minus 2 plus e to the negative 8x. Now, look what's going to happen. Let's look under this radically. Integral from 0 to 1. Here we have our 1. Plus, let's distribute that 1/4. So we have 1/4 times e to the 8x. Okay? 1/4 times e to the 8x. Minus 1/4 times 2. But 1/4 times 2 is 1/2, isn't it? So we have minus 1/2. And then we have plus 1/4 times e to the negative 8x. So 1/4 times e to the negative 8x. Okay? And look, we have underneath this radical a 1/2 and minus 1/2. A 1 minus a 1/2. So what we end up with here, you see, is the integral from 0 to 1 of the square root of, well, 1 minus 1/2 is just a 1/2. So 1/2 plus 1/4 e to the 8x plus 1/4 e to the negative 8x. Now, here's what I'd like to do next. I'd like to have a common denominator and write that as a fraction. We've kind of seen the idea that it's nice to convert a sum under a radical into a fraction, because then we can take the square root of the numerator and the square root of the denominator, but we can't take the square root of terms. So it's a common technique when we have a square root of a sum to try to do something about making that as a fraction if it presents itself that way. So notice what we would do here. We would write 1/2 as 2/4. Okay? We'd write 1/2 as 2/4. So this would be the square root of, and I'm going to rearrange it. We have, I'm going to write it as e to the 8x over 4 plus the 1/2 I'm writing next, but I'm writing it as 2/4 plus our last term, which is e to the negative 8x over 4. Now, this may seem strange, the reason I've done it this way, but I think you're going to see something that happens next. For the integral from 0 to 1 of the square root of something that is a fraction now that has a denominator 4. And the numerator is e to the 8x plus 2 plus e to the negative 8x with respect to x. Now, it may not be clear, but let me come over here to the side. You know, look up here what happened. When we squared e to the 4x minus e to the negative 4x, we ended up with e to the 8x minus 2e to the negative 8x. And if you look at the numerator of our radicand here, the only difference is we have a plus 2 instead of a minus 2. So I'm wondering if that will factor. And so notice in here, if I would have taken e to the 4x plus e to the negative 4x and squared it. Okay, that's not what I have, but imagine if I would have. Then that would have been e to the 4x plus e to the negative 4x times e to the 4x plus e to the negative 4x. And as I expand that, look, e to the 4x times e to the 4x is e to the 8x. So I'd have an e to the 8x first, and e to the 4x times e to the negative 4x, well, it's plus, and that would be e to the 0. And then I'd have an e to the negative 4x times an e to the, see, here's what I did first, here, and then I did this, and now I'm doing this, and that would be e to the 0 again, and now I'm doing this, and that would be plus e to the negative 8x. And that e to the 0 plus e to the 0 is 2. So this is exactly what we have in that numerator. And if I think about this, I can actually do that factoring, can't I? So on the next page, let's continue this problem. So keeping in mind what we just did, we have the integral from 0 to 1 and a square root now, where our numerator is actually e to the 4x plus e to the negative 4x, that quantity squared, and our denominator is 4. Well, the square root of a fraction is the square root of the numerator over the square root of the denominator. So this is the integral from 0 to 1. Okay. Now, the square root of 4 obviously is 2. Now, the square root of something squared, if we know it is positive, then it's just what we're squaring. That is, the square root of that numerator ends up being e to the 4x plus e to the negative 4x. Now, that's only if e to the 4x plus e to the negative 4x is positive. But e to the 4x, no matter what x is going to be positive. No matter what exponent we put on e, we're going to get a positive result. And e to the negative 4x is always going to be positive. Okay, it might be a fraction, but it's always going to be a positive. E to a power is always positive. So we have a positive plus a positive, which is going to be positive, so we can make the statement that we've made there. Well, now you see that we could actually factor out a 2 from this integral, okay, leaving 1/2 times the integral, excuse me, a 1/2, factor out that denominator, so we're actually factoring out a 1/2. So we're actually just needing to integrate e to the 4x plus e to the negative 4x. Now, I don't think that I'll go through these details, but we would do each of those by substitution. See, we use substitution would let u be 4x, and so we're dealing with the integral e to the u, but of course we'd have to make an adjustment because du, at least in the first case, du would be 4 dx. And in the second case, would let u be negative 4x, and so du would be negative 4 dx. But nevertheless, here's you can double check this. Here's what we're going to get. We have the 1/2, and the integral of e to the 4x is actually 1/4 e to the 4x. And we have plus, and the integral of e to the negative 4x is going to be negative 1/4 e to the negative 4x. And we're evaluating that from 0 to 1. But of course, look what we have. We have a common factor of 1/4 in there, and so it's actually a little better, a little easier to deal with if we factor out that 1/4. So we'll have 1/2 on the outside times 1/4 on the outside, e to the 4x minus e to the negative 4x, which we're evaluating from 0 to 1. Okay, 1/2 times 1/4, of course, is 1/8. Now on the inside, we're replacing x with 1 first, so we have e to the 4 times 1, minus e to the negative 4, that's negative 4 times 1. And then subtract, we'll replace x with 0. So we have e to the 0, 4 times 0, minus e to the 0 again. Negative 4 times 0 is still 0. So this ends up being, what, 1/8 times simply e to the 4th minus e to the negative 4th. Because e to the 0 minus e to the 0 is 1 minus 1, which of course is 0. Now, using my calculator, I approximated that to be approximately 6.822 units. Well, for now, I think that will conclude our examples on arc length, and maybe a little later I'll add some other variations. But for now, that's a wrap.